Hi, welcome to the Byrne-Wheeler Report, episode 12. Today we're focusing on memory-related topics. Joining us will be memory analyst extraordinaire Jim Handy, and we will have comments from today's sponsor, MEXT. Gary Spurden, CEO of the startup, will be here. Bob, it's good to see you again.
Good to see you, Joe. And we're recording this on April 3rd.
There were a couple interesting things in the news that I saw, Bob. You pointed out to me that there was Google researchers published something, and then a spinout out of Caltech released an open source model as well.
Yeah, so what was this Caltech PrismML about? I mean, it sounded like it was boiling down weights to a single bit.
Yeah, down to a single bit or, 1.125 or 1.25. I forget the exact value. So the weights are reduced to a single bit, which then take on the value of -1, +1, and then kind of like the block floating point formats, there's this shared value that they get multiplied against. And the key idea here is to reduce memory needs. So your weights, instead of being, say, 16 bits or 8 bits or possibly 4, they're much smaller. They're only a single bit plus that shared value.
So was this targeting like mobile on-device AI?
Yeah, I think the first step will be on-device AI, whether it's smartphones or PCs. And some of the early independent corroboration I've seen has been people playing with it on their, mini or other small system where they don't have a lot of video RAM, but they can run a larger model, taking advantage of the skinnier weights that are afforded by this technique.
I mean, this is a research paper. It's not close to.
Yeah, well, the Caltech folks, they formed the startup PrismML, and this is an open source release of their model. So it's kind of one step past research, but it's before a commercial product. And then the Google paper was TurboQuant, and that's very much research. And I've seen independent people taking the technique and applying it. They're running these on local systems and not necessarily data center scale systems. In both cases, there's still more corroboration needed of the gains. I think TurboQuant said they could get this huge space reduction because they're going down to like 3.5 bits, but with no imperceptible precision loss. But, from what I've seen, people are struggling to keep the accuracy up as they reduce the memory usage.
But in this case, it's actually the KV cache.
That's the big difference. It's not a reduction in the weight size. It's a reduction in the KV cache. And what you give up, though, is there's this extra expansion step because the existing XPUs, their smallest precision is at this point is FP4. And so you have to take the compressed format and then map it into a native format, which consumes a little bit of time with today's hardware. But ultimately, yeah, you can store more items in your KV cache with the same amount of memory.
Yeah. So I guess with MOE in particular, it seems like the weight has the no pun intended, has come off the actual model size. And now in inference, there's a lot of pressure on the KV cache, and that's really impacting, server memory requirements.
Right. I think that's an interesting observation. My other takeaway is that we've had quantization for a long time. It's the whole reason why the hardware started out with 32 and 16-bit support, then it added int 8 and then FP8 and then the 4-bit formats. This has been an ongoing process, and this is, as you point out, these are research papers, so it's not like there's going to be this sudden shift in memory demand in the short run that I expect.
Yeah, what caught my attention was it actually moved the stock price on some companies when this got published, but then people realized that, well, actually the original paper was published like a year ago, and so this wasn't really novel per se. Google hasn't actually disclosed using it in any models thus far. So I think they just announced the Gemma 4 models, for example.
And as far as I know, they don't use this technique. So I guess it'll be a while before it turns up into something deployed at large scale.
So bottom line, unlikely to take the pressure off of memory demand.
Right. I think that's correct. Okay, with that, let's turn to our guests. Continuing with our discussion of memory, memory has long been a contributor of system costs, but now it's become a dominant factor. Joining us today is Gary Smerdon, founder and CEO of MEXT, which has a technology that can reduce the amount of DRAM that a system needs.
Welcome, Gary, and thanks for sponsoring today's program.
Yeah, well, it's a pleasure, Joe and Bob. It's a pleasure, and thank you for having me.
So, Gary, interested to hear what compelled you to found MEXT, and what problem you set out to solve here.
Yeah, so Joe kind of hit it at the beginning here. Memory has become a big issue, but obviously we founded the company 3 years ago, so we didn't know that this true huge crisis was going to take place. But what we did observe and really been studying for a long period of time is that memory, or DRAM specifically, had become an increasingly bigger part of the overall computer cost. And in fact, if you look at 3 years ago, it was 50% of the cost of a server was DRAM. And there's just a little good background on what led us to go, there's an opportunity here. And DRAM is essentially unchanged since when it was first brought to market in 1970 by Intel. One transistor, one capacitor holds a bit. Okay, pretty straightforward. Every other major component in the server has gone through major revolutions where DRAM is unchanged, but it's still continued to get better and better from a cost per bit standpoint over the years until Moore's law relative to DRAM came to an end about 15 years ago. So we no longer have the ability to see that reduction in cost because a fab can make twice as many bits, 4 times as many bits if you go 2 years, 4 years, or on and on. So this just kind of led to this trend that this problem was not going to be solved anytime soon. It seemed like a good opportunity to take it on.
Okay, so what does MEX technology do?
Yeah, so MEX technology, first of all, we're just software. And there's kind of 3 key things that we set out to make sure we could do. Number one is we wanted to make sure we could increase DRAM utilization. DRAM had become 50% of the cost of a server. That's bad, but what made it worse is that it was really and has been historically poorly utilized. In fact, there were studies in 2022 by Meta, Azure, Google, as well as our own experiences that led us to see that over half of the DRAM was either not being accessed at all or not being accessed for long periods of time. And so what could we do about that? So we wanted to, number one, increase DRAM utilization. Number two is I wanted a solution that had no hardware or software changes from an application or operating system standpoint, because as a startup, that slows adoption, that adds risk, and it takes cost in the wrong direction. And our number one objective was to increase basically capacity of DRAM and lower cost. So that was pretty compelling. And we actually thought about starting the company just with some really good ideas to go after that. But the big third idea was, gosh, can we bring flash into the memory tier and do it in a transparent fashion? Why? It's 50 times cheaper per bit. It's also 30 times lower power per bit. So that would be a game changer if we could do it. And that's where we kind of came up with, hey, can we use AI to take on this problem? And that's what led to the founding of MEXT.
Can you kind of give us a quick explanation of how this solution actually works?
Yeah, so happy to do that. So there's 2 main components to MEXT. One is just a driver that's loaded in a Linux driver that is loaded in. The second one is an AI engine. And this AI engine is there looking at what's happening from a memory usage standpoint. And it allows us to identify what pages are hot, what pages are cold. The cold pages we're able to push off to flash. That's not really that big of a new invention, but still an important thing that we do and do really well. But the big thing is that our AI engine monitors what's going on and proactively pushes the pages back to DRAM prior to them being requested by the operating system or application. And so it's all transparent, and it allows us to essentially, number one, we can lower the amount of DRAM in the system and make it up with flash. So a 50-50 ratio is common, but we can also just take a system and double or triple or quadruple the amount of memory that the application is seeing.
So how well does this actually work?
Yeah, so the short answer is it works great, but that's easy, and you would expect me to say nothing other than that.
Right.
The reality is that we've done a lot of internal testing. We've also been working very closely with customers and partners. And in most cases, what they basically come back and say is that we can do the default of doubling the memory in the system. And when we run our applications, the result is that there's negligible, if any, performance degradation that they are seeing. So the benefit is, basically able to lower the cost while, of course, maintaining performance in the system. And we've been doing that across a bunch of different workloads. And so we have great confidence in what we're doing.
So could you clarify something? You said something about doubling the memory. Could you just explain what you were stating there?
Yeah. So when you start MEXT, our default configuration is that we'll look at how much DRAM is in the system, and then we will identify an NVMe flash drive in the system. And however much DRAM is there, we are going to double it transparently. So transparently mean the application didn't know that all of a sudden this half a terabyte system is a terabyte, half a terabyte of DRAM, half a terabyte of flash that has been made to appear as DRAM in the system.
Gary, can you talk about some of the, specific applications or use cases where you're seeing kind of high quality benchmark results?
Yeah, and I would say more important than benchmark results, customers' results is what we, of course, care about the most. But it's pretty widespread. EDA is a great example. This is a memory hungry workload. It's very compute intensive as well. And what we've seen is that we have had customers where they have either doubled the amount of memory in the system and run twice as many jobs simultaneously, or taken a system with half of the DRAM, increased it, and when they compare it to one that was all DRAM, it was basically at 98, 99% of the performance of the full DRAM system. So EDA is a good example. Major movie studios using us for animation and doing their benchmarks looked great. But more importantly, turning it over to the animators and saying, work with this system, work with that. Can you tell a difference? And the answer coming back as no. But because of where we sit in the system, it's important to understand that we don't know what's running on top of us. And I can go into how our AI works because we don't pre-train, so we don't have to know what's running. And so we are able to turn it over to a customer. They're running an analytics workload. They're running a graph database. We don't necessarily know. We just know that they're happy and moving forward.
And Gary, that means also that they could be using the graph database at this moment, but then using the exact same hardware to run another application, right?
Absolutely. That's exactly right. So we are generic from that standpoint. Probably makes sense for me to explain our AI engine and some of the key aspects of it real quickly. So when we think of AI, we think, of course, and we are using multiple models, but a transformer-based model, same as ChatGPT, is kind of our workhorse AI engine. And unlike when we talk about ChatGPT and the others, they go through a major training step on special hardware that usually takes days, weeks, months. And then they do inferencing, typically on different hardware. And that, of course, is the real-time interaction. We do training in real time. So the reason we do that is because the same application with a different workload or different uses taking place can behave very differently under the hood. And so we have to do continual training. When you start us up, we will start making very good prediction in a matter of a few seconds. And then we'll continue to get better from there. Now, of course, we are doing inferencing, which we call predictions, and those are the predictions to push the pages back into DRAM, and we do that on a continual basis. And so continual training, continual inferencing or predictions. The big thing that we've accomplished is to do this on just a single processor core, not a GPU core, a single processor core.
And so this is different from transparent page placement or regular swap in that there's a predictive angle in terms of what you swap out or push to the other memory tiers. Is that fair to say?
At 50,000 feet, you may say they're kind of similar, but they're very different. It's with the AI engine that's able to adapt and adjust to what's going on. That's why when you look at these other technologies, that's why they're not used that often too, is because they don't perform well. And even if they're performing well at a particular instance, things change and all of a sudden they're not performing well. But there's another subtle difference as well in that with traditional Linux swap, for example, the application knows that swap is taking place. In fact, if I
Right.
use that example of a 0.5 terabyte system, which we made to look like a terabyte or 2 terabytes, in that example, the application only sees a 0.5 terabyte of DRAM. And so it modifies its behavior to go and act in a way that is consistent with that. Where with us, it would see that full 1 terabyte or 2 terabytes of memory, not realizing exactly where this transparent placement is taking place.
So, Gary, kind of looking at the future, what are the other kind of applications or use cases where you think the technology will provide it?
Yeah. So, as a startup, we have of course focused on servers and some of the applications that are particularly memory hungry. But this is when we founded the company, right? And then, of course, this memory crisis where we've seen, this week a customer explained to me that, and they're a really big customer, that they've seen their server prices go up 5x since November.
Wow.
So
Just to be clear, you're not saying the memory cost went up 5x.
I didn't say the memory cost. I said the server cost has gone up 5x. And there's some of them is, it's unbelievable. None of us have ever seen anything like this. So with that, we now have customers and partners really looking to go, okay, there's a lot of other use cases, right? Different form factors, different operating systems, much, much lower end type of applications that there's interest in addressing as well. And over time, this is, in our view, the future of memory because it makes no sense. We didn't have innovation. DRAM's not advancing. We got to do something. We believe this is a great, if not the best answer.
So where can our audience go to get more information about MEXT?
Yeah, so our website is the best place to start, and it's just MEXT.ai. So MEXT.ai. Love to engage with more customers and partners.
Thanks, Gary.
All right.
Appreciate the discussion and appreciate you sponsoring the episode.
My pleasure, and it's always great to see you, Bob and Joe. Thank you.
Joining us now is friend of the show, longtime friend, and longtime memory analyst, Jim Handy. Welcome, Jim.
Good to be with you too.
So, Jim, I was wondering if you could quantify for us how much memory prices have changed over the past 6 months to a year and how this is compared to other past memory upcycles.
If you look at spot market prices, which are the most visible place for the changes, and the spot market, just to make sure you take it with a grain of salt, it's always a little bit more, or a lot more extreme than the contract market. But, in the spot market, we've seen DRAM prices go up by about 4 times since September of last year. And NAND flash has seen prices go up by about 7 times since about October. It was a little bit later than DRAM to take off. So, this is something I don't think I've ever seen prices quite go as extremely as that over the course of my career.
So, Jim, thanks for being here. How is this affecting the bill of materials of systems and products like smartphones, PCs, servers?
What's interesting, servers tend to be very DRAM heavy, and so this affects them more than anything. But in PCs and smartphones, there's some interesting tricks that can be played there. The OEMs who make PCs and cell phones, they take advantage of the fact that they can provide to the consumer something that is a larger memory than what they had in the computer that they're replacing or the cell phone that they're replacing, which is going to be between 2 and 5 years old. And so what their plan was, I think, before this memory rise happened, was that they were expecting for this year's memory sizes to be maybe half again as large as last year's memory sizes. Instead, what they're doing is putting together systems that have memory sizes that are the same as last year's. And since the users haven't bought a PC or a cell phone for 2 years or for 5 years, they're going to look at their 5-year-old unit and they're going to say, oh, well, this is a handsome upgrade of memory from the amount that I have in my old unit. Another thing that works is that the bill of materials for a PC is probably somewhere in the order of 30 to at most 50% DRAM. And so you take the DRAM and, let's say it goes up by 100%, you only feel it half of that 100% price increase when that happens because of the fact that the rest of the bill of materials hasn't gone up that much. With cell phones, a cell phone manufacturer might put in an extra $3 worth of NAND flash and then charge, $100 extra for that particular cell phone. And when they do that, then they have an awful lot of margin in there. And so they, they're going to take a margin hit when the prices go up, but it's not going to be that much. In the case of 100% price rise, and flash would go up by double, it would go from $3 to $6. They'd charge $100 for it. That their margin's not really going to go down that much.
Yeah.
In the server, it's a whole lot more cost-based pricing. And so what I'm hearing from people with servers is that the server prices are going up, and also that it's hard to get certain models of servers that you used to be able to get with the large memories, that you actually have to buy the memory separately. And anybody who buys those memories, they're buying the memory by itself, and they're going to see this huge price increase right smack in their faces. So that's a big deal for them.
Because they're in the spot market. They're not contract buyers.
The spot market does play into that to a certain degree, although large memory module manufacturers like Kingston Technology actually have regular OEM relationships with the memory manufacturers. It's up to Kingston to decide whether they want to charge the kinds of outlandish prices that you see on the spot market. If they don't charge something equivalent to the spot market prices, then they'll get completely bought out by the people who need high volumes of, product, that just can't seem to be getting it from the DRAM manufacturers.
So can you explain then why there's this kind of 3-to-1 ratio in terms of bits actually net for HBM versus DDR?
Yeah. And that's called the trade ratio in the industry. And it sets how many gigabytes you're going to get on a wafer. A manufacturing plant can only produce so many wafers. So you've got this resource that's shared between HBM and DDR. HBM, because of the fact that it needs to be stacked and it needs to have these through silicon vias. Through silicon vias take an awful lot of room on the chip. And so you might have a DDR chip that's a certain size that holds a certain number of gigabytes of memory. And that same chip, once you decide that you're going to be building it as an HBM, then the design actually has to expand because they put all of those TSVs right in the middle. And it makes the chip more than double its size. Now, that's a problem by itself, but then something else is that there is a little bit of a yield issue with that. The larger the die you try printing on that wafer, the more likely that die is going to have one of these defects in it or two of those defects in it.
Do the yields also decrease as you increase the stack size? Going,
that's
8 to 12?
Yeah, and that's a packaging issue, and those tend to be things that are relatively quickly solved. Processing issues tend to be a little bit more hairy than the packaging issues. But I don't want to belittle the guys who do packaging. That's just a very advanced technology that they're using to stack those things up, because they have to take that wafer and they etch the holes into it, but the holes don't go all the way through the wafer. And then they have to fill the holes up with metal, and then they back grind the back of the wafer down to the point where it's very, very thin. You can actually take the silicon wafer, which is like a piece of glass, it's brittle, it's rigid, and you grind it enough and it becomes so flexible that you can roll it up to the size of a cigar. Now, 12-inch wafer is going to make a heck of a long cigar. They need to do that because they're stacking these things 12 high, 16 high. They're going to be doing 16 for HBM4. And when they stack them that high, then they are packaging them together side by side with a GPU or a TPU or an XPU, whatever it is. And you want to make sure that because you're putting a heat spreader across the top of all of these chips, that you don't end up with an HBM stack that sticks way up here that keeps the heat from getting drawn out of the GPU. So you end up thinning and thinning and thinning the wafer so that you can get it so that the stack of 12 or the stack of or whatever DRAM chips in an HBM is no taller than your GPU.
Okay. So for how long will prices keep going up? Or maybe I should frame it as, what is the factor that's going to reverse this trend?
That's two very different questions. I'll answer them as two separate questions. The first one, how high can that go? That's something that, so far we're nowhere near the limit. DRAM prices could go sky high. What happens then is that certain companies that buy DRAM would end up going out of business. And the question is, how high can prices go before the market ends up self-limiting by having companies go out of business or be unable to sell systems because they're too expensive. We're not there yet. So it's very reasonable to believe that prices could go significantly higher than they are today. As far as what would cause that to undo itself, the thing that's really driving the shortage is that there is massive AI spending going on right now. And AI is consuming a whole lot of these HBM DRAM stacks, which, as Bob pointed out, the HBM is not as efficient with the wafers as regular DDR is as far as making gigabytes on a wafer. And so that means that, the capacity gets gobbled up a whole lot faster when AI starts ramping. I like to argue that even if AI didn't use HBM, if it were just using DDR, it still would have created a shortage. It's just creating a far worse shortage because of the fact that it's using HBM. So we've got this DRAM shortage, and what is going to cause that to go away? Well, the DRAM manufacturers are building fabs, but it takes about 2 years to bring a fab online from the time that you first break ground until you're actually in volume production. So that's something that automatically makes them unable to keep pace. The DRAM manufacturers are getting orders and forecasts from their customers that keep growing. And so they plan their fabs out, 2 years in advance. And then the customers say, oh, well, we were wrong with that forecast. We need a whole lot more than what we said before. And so the DRAM manufacturers have to plan for more capacity adds. And that means it's going to be another 2 years before they can accommodate that adjustment. And then the user comes back again and says, well, now we need to increase our forecast again. And that's a kind of a situation that we're in. They're not going to cause supply and demand to come together with their spending just because of the fact that you've got that lag and you've got the unpredictability of the forecast. And so the only other thing that is likely to cause the market to stop having rising prices is if AI spending slows down. And we don't see any indication that's going to happen. I made a presentation at a conference a little over a year ago, where it showed that for 6 major hyperscalers that their quarterly capital spending was around $70 billion per quarter. Then this year, early in the year, I made a presentation to the same group that capital spending had almost doubled. It was over $135 billion per quarter. How in the world do you keep pace with that? If these guys, let's say, like what happened with the internet bubble, that the AI guys say, hey, wow, we built too much. We've got too much capacity. Let's just not do any more capital spending for a quarter. And if they were to do that, then all of a sudden the market would be oversupplied and you'd see prices come barreling down the way that they do typically in, whenever there's a memory oversupply.
Would one quarter really do the trick, or would it be sort of a multi-quarter correction?
Yeah, it typically takes about 2 quarters for prices to come down to cost. So it's very fast, but yeah, it wouldn't happen in a single quarter. But what I'm saying about the quarter is if there were a quarter where the AI guys stop spending, then, that would be the case. And, because all you got to do is you've just got to, it's kind of like it's the spark in the area that's about to explode, that stopping spending causes the whole pricing thing to kind of unravel very suddenly. Bob, nobody's asked me that question before. The best example we have of how that can happen is the 2008 global financial collapse. Electronics didn't really get phased by that all that early. It still wasn't until about January of 2009 before the semiconductor world felt it. And boy, when they felt it, it was just like, bam, demand completely evaporated for a month. Maybe it was for 2 months. And that caused the prices to completely unravel. The demand came back late in the quarter, but that wasn't enough to recover from, what had started.
Thanks for your insights, Jim. Where can our audience get more of your insights and your analysis?
We have a website, Objective Analysis. It's objective-analysis.com, and where we show our reports and where we talk about what we can do from a consulting standpoint for customers, clients, and also, we do consult with people through GuidePoint and other expert networks. So, appreciate anybody who would like to come. We try to give the best service we can.
Absolutely.
Well, Jim, memory is a world unto itself, so thanks for lending your expertise here.
Well, thank you very much, Bob. Thanks, Joe.
Okay, we'll talk to you again. Thanks. Bye-bye. This has been the Byrne-Wheeler Report. Until next time, be well, and in the meantime, check out one of our other episodes.